It's running. Okay.
Let's talk about this. So first off, what kinds of spatial data can we have? And generally when you talk about something, it's going to be an object in space that is going to have several different components to it. It exists in 3D space. Oftentimes we're looking at things in 2D space because that's, for whatever reason, how humans decided we like to map things way back in the day, or like how we like to think about space. We don't like to think about it in 3D on paper as much. But one of the things that we can do is we have these things that have area. And we've talked a little bit about that. However, that being said, areas are not normally, or not often, what we actually want to know about something. I mean, we do sometimes. Oftentimes, one thing that's more interesting is where something occurs, and defining it by a point. So we can say, like, this person is here. Doesn't really matter how much area that person has. I want to know where that person is at. Or like, this animal is at this location. Or this instance of something else. So these are called points. They're also sometimes in spatial data analysis called events. I don't know why. And we can define them usually by some sort of XY coordinate system, be this latitude, longitude, XY, and like UTM, something else like this. We define them by 2 coordinates in some 2-dimensional space. And this can be all sorts of things. For instance, it can be occurrence of an organism. It can be like an incidence of a disease. It can be like an actual event, like, hey, a fire happened here, this house burned down, or this crime happened here, something else like this. So this is kind of the type of data we're going to be considering today. And one of the most interesting things about this then is when we consider them in populations and we consider about them what's known as their spatial homogeneity. And spatial homogeneity can have we can break that up into 3 different kinds of organization. So first off, the incidence of points in a landscape can be random. There can be no underlying order to where they occur. And this is what's known as being completely spatially random, or CSR, or just random. Alternatively to that, they can also be regular, as in they are occurring at somewhat regular intervals. They're not occurring randomly. There is some sort of process that keeps them in some sort of regular, spaced out area. And we'll talk more about this, and I'll try to give you examples of these. And they can be clustered as well. They could actually be occurring more closely to each other than you would expect randomly to happen. Okay, so let's take a look at this. And one thing I do want to just kind of tell you about is people are really bad, actually, at defining these, like looking at them and knowing what's random, what's regular, and what's clustered. People, like most kinds of data, you can look and see if they're non-random. Spatial data, you are horrible at. Which one of these 3 does this look like, by the way? You think it's random? Anyone else have an idea? Okay, so let's go down that list. The first one was random. How many think this is random? Okay. How many think this is regular? 1. How many think this is clustered? 2. Okay, so I had like a lot of people for random, 1 person for regular, and 2 people for clustered. This is actually regular data. This is not random. What about this? What do you think this is? Think this is random, regular, or clustered? How many people for random? 2. Okay, a decent number. Yeah, just call things random until you eventually get right. That's good. How many think this is regular? Okay, good. How many think this is clustered? Okay, so we're like split half and half on random and clustered. This is random. How about this one? At this point now, how many think this is random? Okay. How many think this is regular? Taylor thinks it's everything. How many think this is clustered? Oh, hey, good. We're getting the idea. Good stuff. Let's look at another one. No, this one. How many think this is random? Okay, 1. How many think this is regular? 1. How many think this is clustered? Like, a bunch of you don't even want to call it anymore.
Give up.
How many give up? This is, okay, so this is actually clustered again. Okay, let's look at this one. How many think this is random? Okay. How many think this is regular? Okay, more of you. How many think this is clustered? Okay, no one. This is random. Okay, so the underlying point being is that for whatever reason, people are really bad at spotting order in things unless they're like all lined up and actually in rows or something else like this. People are bad at spotting spatial organization for whatever reason. And I think probably one of the fundamental reasons for this is that actually it's not that you're bad at detecting spatial organization. The problem is that you're actually too good at it, and you're bad at seeing randomness. So people tend to look at things and try to think that, oh, that looks structured, that looks clustered, I see clusters in there, I see some sort of pattern in there, and then it throws everything else off. I don't know, that's just my little theory about that. But whatever it is, people are bad at picking these out. So if you got every single one of them wrong, except for the one clustered one, the third one, don't worry about it. Most people do. Okay, so how in the world can we go about actually detecting these? How can we go through this and decide what is random, what is regular or dispersed, and what is clustered? And this is important. This is a really important thing to detect, because underlying each of these, underlying a non-random distribution is some process controlling that. There is something that makes spatial distribution non-random. And there is something interesting to be figured out when data is not spatially distributed. If they're clustered, there's probably something clustering them. If they are regular or dispersed, there's probably some sort of inhibition process that is preventing them from being close. Like, for instance, if you were to go out to like into the deserty area between here in Tri-Cities, like you stop off at McNary Wildlife Refuge, and you were to look at bunch grasses where you have places that are predominant bunch grasses, they are regularly spaced. It's because there's a biological process in which they're inhibiting each other from growing too close to each other, and that keeps them from getting too much competition with each other. So they prevent other things from growing really close. And so when you have these different non-random things occur, that's really interesting because there's something else happening. Okay, so there's a couple different ways that we can detect these, and the two that I'm going to talk about here today, I'm going to talk about two general categories or approaches to these. I'm going to talk about quadrat analysis and neighborhood analysis. Now, each of these I'm just going to talk about one or two ways that we approach each of them, but I want you to recognize there's actually many more different ways I'm not talking about here, and I'm just going to try to pull out what I think is the most important of these, the most widely used, and ones that will give you a good idea of how, if you understand these and you encounter a new one, you will have a rough idea of how it's working. Maybe not exactly, but you will get the idea. So let's begin out here with quadrat tests. Now, just give a little bit of background and overview of what quadrat tests are. First off, these are the older of the spatial analyses. These predate computers. We were doing quadrat analyses before we could use computers to get things more easily. And so they're fairly, I mean, they're not easy to do by hand. I wouldn't give you anything really bad to do by hand this way, but I might give you a small one to do by hand at some point in the lab or something like that. But you can do them by hand. It's not impossible. Actually, the math is fairly simple. And what you do is you simply divide the study area into equal size squares. So we're going to divide up whatever the area that we have measured something in. We're going to divide them up into the equal size squares and try to take a look at those. And generally, we count the number of events in each square, so that we can get some idea about how many individual occurrences are in each of these squares. Once we have that data, once we have a number of quadrats and how many points occur in each of those, we can do some fairly simple analyses on these. For instance, we can simply compare the number of expected, the number that are occurring in each quadrat to an expected value. And when we do that, we can do something simple like a chi-squared test. If you're unfamiliar with chi-square, well, if you're unfamiliar with chi-square, you just remember essentially what we're doing is this is a statistical test on count data where we can compare count data between different groups or areas or something like that. Where simply we generate some expected, usually this is like the average or something else like this, and then the chi-square test then tests how this distribution, how far is it from being random or far from our expected values. Now, one thing to kind of keep in mind is our null hypothesis when we do this is that the points are randomly distributed. So above that, that is the hypothesis we're starting with, and if we reject that, then our alternative hypothesis is the points are not randomly distributed. The expected that we can generate then for each number is essentially the average of what we expect. So just the total number of points in the entire area divided by the number of quadrats. So for instance, if we had 100 points and we had 25 quadrats, then it'd be an average of 4, or our expected would be 4 points for each quadrat. And then we can treat each quadrat like a cell in a contingency table after that. We can just calculate this up like we would a contingency table, essentially adding up the chi-square value for every single one. Just as kind of a reminder how we calculate chi-square values, it's the observed value minus the expected all over the expected value, and all of this squared. So for instance, if I had 5 in my previous example, we have 100 points. We have 25 quadrats. I had to accept 4 in each. Imagine I found 5 in one of the squares. It'd be 5 minus 4 all over 4. Or observed minus expected all over expected. Square that. So what we get here is 1 over 4, and that squared gives me 1 over 16, or what is that as decimal? It's 0.0. I don't know. Anyways, so that would be our chi-square value for that one cell. And we'd add them up for all of the cells and compare that. Then generally you compare that to a chi-square table. So let's look about how this would happen. Go here. Yes. Okay, so here is one of these. What does anyone remember what this was? Does this look random? Is this clustered? Okay. Yes, this is clustered. Okay, so imagine we take this and we divide this up into quadrats 5 high and 5 wide, so 25 of them. There are 100 points in here, so we could do that. So we can divide it up into these equal sized quadrats, and now we have these individual cells in which we have the individual numbers of points per each one. Now we can take those, and let me go into R here, do some fancy stuff. And the nice thing about like chi-squares in R is that you can just do them and not like wait for things to. Another kind of nice thing here is that we can, there is this. So this is actually that point process I did right there. Let me zoom in a little bit on this. View, zoom in, view, zoom in. Yeah, that's okay. View, zoom in, view, zoom in. Okay. Okay. So go. There's this nice quadrat count function right here. And all you have to do is like put in your thing that has your object that has your XY coordinates in it. Tell it how many quadrats high, how many quadrat wide, and it'll actually do the count for you. Okay. If you have the right library. You have to have the SpatStat library. Oh, what? Okay. Are you serious? Did it really not save a... That's embarrassing. Okay, so let's do that quadrat count. So if we do that, it generates... Now this is now a different random thing, but it will generate actually the counts for all the cells for you. And then if you just want to run a chi-square test on that, you can just save that as an object and then run a chi-square test on that. And it gives us a p-value here. P-value is 0.0225. So what does that tell us, a p-value of 0.0225? It's not random. Does it tell you it's clustered? No. At this point, we have no directionality. We know it's not random, but we don't really know that much else about it. Okay, I'm actually going to run one more thing because I need to for the next example. CSR. I need you. Okay. Okay, so let's take a look at another one. Here's our regular data again. And so we divide it up the same way. And you notice that this looks different than this. Here we had like 0, 0, 0. We have 12 here. We look at our regular data now. We have 3, 6, 4, 2, 5, 4, 4, 5, 5, 2, 3, 4, 2, 3, 5, 5, 4, 5, 4, 5, 1, 5, 8, 3, 3, 5. You notice how that's different than what we had before. So here, how do you think chi-square is going to perform at finding regularity here? You shake your head, Matt.
Shake my head.
Why do you shake your head?
Because they're just spread all over the place in those quadrants, and somewhere on the lines,
Yeah.
quadrants too.
Yeah. But then it counts it because, like, honestly, this is like an infinitely small point, so it counts it like where it actually is. So, that, like, on the line isn't too bad. It just counts it where it's actually in, like where the center's in. But the thing here is, and let's go back to R here for a second. If we run this, this is actually not good. All of these quadrats are very close to what we'd expect. So if we run a chi-square test here, our p-value is 0.5404. Can we reject the null hypothesis here? No. So, which leads to talking about what's good and bad about this test. Let's talk what's good and bad about the Quadrat chi-square test. And the pro is as easy to do, and you can do it by hand if you need it. That's kind of nice. I mean, you could give someone a bunch of points, and you could sit there and like you could do this with a pencil and use your ruler and draw out your little quadrats and like count up all the cells and do a nifty little chi-square and go look it up on a chi-square table, and then you have a p-value. That's nice. The problem is that, number one, your answer changes with the number of quadrats you have. Imagine this. Imagine I had so many quadrats that any one quadrat only had, like the quadrats were so small that any one quadrat only had 0 or 1 point in it. At that point, do you think you could reject the null hypothesis? You couldn't, because no one quadrat is getting filled up more. If all quadrats only have 0 or 1 point in it at a very fine scale, that's no different between randomly distributed data or not. The other thing is, if I go up to the very largest size, imagine to another extreme, the very largest size, where you just have one quadrat, the entire area, you have your expected number in the entire area, which makes sense. So it's the whole number divided by 1, which is exactly what you have, lo and behold. So the problem is that your p-value is very dependent in this case in how big you make the quadrats. Now, there's some rules of thumb that you can kind of follow, but the problem is that oftentimes we have different spatial processes happening at different scales. Sometimes, at a very small scale, you can be random. Like we could have that kind of random. But then as we blow it up, then we have that's random, and that's random, and you have clusters now. Within each cluster, they're random, or maybe within each cluster, they're regular, but you can't detect that with this. And what the answer that you get will be dependent on whether or not you have squares that capture the clustered process or the random process, or the regular process. So that's the problem. The other problem is it doesn't detect regularity. We can't detect anything where they're spread out evenly this way. It has no power to do that. So let's talk about an alternative that at least takes care of one of these problems. And that is the Poisson test, or this is what's often just called the Quadrat test in spatial statistics. And what we do is we take the number of cells with each count number. We take all the zeros. How many had 0? How many had 1? How many had 2 points? And then we compare this distribution to a Poisson distribution. I'm not going to get into why this is, but I'm just going to give this to you as something to accept for time's sake, is that we know that if things are distributed this way, that the distribution of the number of cells that have a particular number of points in them should follow a Poisson distribution. And again, we can just compare it to this with a chi-square. So again, here we have our regular data. Let's use that as our example since we failed at it last time and we feel like failures, so we want to tackle it again and show we're not failures. And so we have this. So for instance, we look at this and we have one square that has 1 in it. We have 1, 2, 3 squares that have 2 in it. We have 1, 2, 3, 4 that have 3 in it. And what we can get is we can get a distribution like this. We had no squares that had 0 in it. We had 1 square with 1 point in it. We had 3 squares with 2 points in it. We had 5, okay, I guess I missed one, with 3 in it, and so on. And we can now compare this to what we would expect based on a Poisson distribution. And that looks like this. So what we have here is a Poisson distribution would expect this. Now these are all fractional numbers, so it doesn't give you exact counts. But here's something now that will happen. If we are regularly spaced, how do you think this would look different than random? Imagine just for a second, they are all perfectly evenly spaced, like they are on a grid. How would the observed distribution look in that case?
Just be a spike.
Yes, you would get to your average and it'd just be a spike. You'd have like all 25 right here, and basically everything else would be at 0, right? For regular data, you tend for the middle of the distribution to be higher than expected, and the tails to be lower. For a clustered distribution, you expect the opposite. You tend it to be more flat out. You tend to see it being higher than the expected on the tails, and lower in the center. So then what we can do is we can, again,
Is that like a definition for what regular and clustered data are?
in this case. There's different ways to define, so the definition, and really the definition is we're just doing everything in probability. So what we're talking about is how probable is it that you could generate random data and achieve this kind of distribution. And so that's what we're trying to approximate in all of these. And these are simpler ways than probably something you're thinking about. Why not just generate random distributions and see what the probability is? And that's a better way to do it. But for the moment. But yeah, so it's not like we're defining it that way. We're trying to estimate what the probability of a random process achieving this kind of distribution. Does that make sense?
Yeah.
Yeah. Let's talk about this. Okay, so we have those different things that we would see, and we can look at each of these versus chi-square. So we can actually take the difference of the observed minus the expected over the expected squared again, add them up for all the different bins that we have here, and go ahead and do a chi-square again on that. Okay, there are some pros and cons of this. Pros, so it's still easy to do. You can still do this by hand. Hooray! And you can detect both clustered and regular data. That's awesome as well. The cons, however, is it's still very affected by quadrat size. Again, you could imagine us getting so small that every single quadrat only had 0 or 1 point in it, and it would fail at that point. Again, we could just have one quadrat for the entire thing. Now, these are extreme examples you would never actually do, but just to show you at the tails, you know, of what you could possibly do, it fails spectacularly. If you have just one quadrat, again, it fails completely there as well. So, in lab, I'm hoping to have you kind of see for yourself, if you change the quadrat size, it's actually fairly dramatic. Like, if I go from 25 to, like, say 36, you can get wildly different p-values for this and for the first one. So that's something to keep in mind. Okay, so that leads us into the next. Okay, so that's all for quadrats, and that's one basic way that this gets accomplished. But there's another way in which we can do this, which is a little bit more refined, more awesome. And that's some neighborhood approaches. And so what we can do here, well, first off, I'm going to say these are newer. These are harder to calculate. They take more time. The reason for that is instead of using quadrats, we're actually using the distance between the points. And this, you can, I mean, if you had XY coordinates, you could still do this, and you could, like, add them up, and if you get up to, like, thousands to hundreds of thousands of points, this can be, like, again, you could put, like, one grad student on it for their entire 4 years of their PhD and be like, okay, give me the pairwise points between all of these 10,000 points. Yeah. Maybe just take a month. I don't know. And so let's talk about some of these. Now, the first one I want to talk about is a nearest neighbor analysis, or which is also sometimes called a D1 test, or a nearest neighbor D1 test. D1 because we're talking about distance and the first distance, or the smallest distance, therefore the D1. And for what we do here is we find, for each point, we find the distance to the nearest other point, and we take that. And again, what we can do then is take all of these different points and find the distribution and how close the nearest point is to all of these, and compare this distribution to by a Poisson distribution by chi-square. And I'm not going to show you exactly not this because I want to get on to the next one, but just to know it exists, and I'll have you do it a little bit in lab. The pros of this is this detects regularity very well. Because again, if you have an inhibition process where things can't get so close, it's really easy to test that by looking at what is the shortest distance between points. And actually, this is so robust that you can actually get a statistical determination of the distance of inhibition. Like what is the distance at which these points begin inhibiting each other from occurring closer to each other, which is kind of nice with this. The cons of this is that it does detect clustering, because again, if they're clustered, you're going to get that distance going shorter and shorter and shorter, but it doesn't necessarily do it great. Actually, it turns out that some of the quadrat tests are a little bit more robust at detecting clustering. It can do it, not the best for doing it. And then here's the other thing, like all neighborhood analyses, it needs a correction to account for edges. Edges screw up neighborhood analyses. And let's talk about why that is. Let's imagine right here, this point right here. He's kind of far away from all these. But here's the problem. We are in a sample area. We don't have the real world right here. What we have is some fictional boundary here that we have for some reason set. And if it's not a real boundary in real life, it's very possible that there's another point just out here that's closer to this point than either this point or this point. So for that reason, this is going to skew our data. As we start looking for nearest neighbors, all of these points along the edges are going to start screwing that up. Now, one thing that we can do, a couple corrections that we can do, is like, well, one thing we can do is we can just consider a buffer around here. And then we're only going to consider all of the points within that buffer. So now we don't actually have anything on the true edge, and we know what is beyond there. Problem with that is that we're throwing away data. It might be a more true estimation, but we're throwing away data, and we're throwing away our ability to detect spatial processes. The other, and this is more common, and this is just to give you a couple of flavors. There's actually so many different ways to correct for edge effects, but I'm just giving you a couple just to kind of give you the idea of types of things people do. Is to do what's called toroidal correction, where essentially it loops back on itself in every dimension. Or another way to think about this is if we just take that point process and copy it all over, like for each Queen's case difference. So for instance, we take it and we copy and put it over here, we put it down here, we put it up here. So for instance, we have this point, and now it's over here. So for instance, here now, instead of this point being the closest point here or here, it's now this right here. And so this is another way of correcting for edge biases that creep in. You won't have to calculate any of these or actually manually do these, but you need to recognize that there's edge corrections and how to use them. Okay. Let's talk about now Ripley's K and L. And this is a neighborhood analysis that detects both regularity and clustering very well. This is probably the most used statistic for detecting these kinds of spatial processes. And let's talk about what this is. Instead of just using the nearest distance, which kind of gave us a limitation on the D1 test, we are going to use all pairwise distances between all of the points. And so how we do this, so first off, let's define a couple terms. First off, you can imagine a point process that has a density that we are going to define as lambda. So this is just how many points per unit area, and that is lambda. And then our statistic here, we're going to start with the Ripley's K statistic. K of t is equal to, t being, we'll come back to that because it's in here, is 1 over the density times the number of events that you can expect within a distance of t from any randomly chosen point in this area. So if I had a point process here, like this, and I chose some random point, let's say this one, and I give it a distance t from here. At distance t, based on what we'd expect for a random distribution, what can we expect being, so how many points can we expect to be in there times 1 over the density? Now this is simpler than you think, and let me show you why. So it's really easy to figure out how many we can expect to be in here. If it was a square, if I had a square with, let's say it was 2 on one side and 2 on the other side, how would we figure out how many we could expect to be in the square? Yeah, multiply the what by the density? The area. Yeah, you just multiply the area by the density, and that gives us how many we have in there. So that's the same thing we do here. All we have to do is multiply the area by the density, and that gives us how many we can expect in there. It's really easy, and we can figure out the density because we have the radius. So again, we have the area times the density, and then as we define it is times 1 over this. And so this is just pi r squared, but in this case we're defining t squared, so pi t squared. Nice thing is, this 1 over the density times this density cancel out. And so the expected KT is just the area of the circle that it inscribes. And that was intended here. So it's really easy. The expected for random data for any KT is just the area of the circle that's inscribed by that radius of that distance. So we know what to expect from random data. We expect the KT to simply be equal to the area of the circle, and then we can look at this for various levels of t. So we can go a short t, a bigger t, a bigger t, and then we could actually see what it should be. But we can also calculate for what it actually is for our data as well. So we calculate. That's how we determine that equation is how we determine the theoretical, or what random should be. We determine what our KT actually is for our data by finding all of our pairwise distances between all of our points. And then what we do is we can then say, for increasing values of t, we take the count of the number of point pair distances that are less than t times 1 over the density, which gives us the same thing. So essentially we're saying, if I have a bunch of pairwise distances that are lower than 1, I can count those up. That is roughly equivalent to how many I can expect, how many points I can expect, divided by the density, or times, but divided by the density, or times 1 over the density, how many points I can expect to get from a random point with a diameter of distance 1. Okay, so let's take a look at this and how this actually looks. If we look at this, again, this is our regular point pattern. Does this show up well? It shows up horribly. Okay. This is our K statistic, and you can barely see it. I am very sorry this turned out this way. But you have a little blue dotted line right here. That is our theoretical. So again, we're going length in area. So as we increase by distance, so this is 5 units out, this is 10 units out, this is 15 units out. This is the number of points I can expect to be within that distance divided by the density. Hold on. This is our K statistic here, or our theoretical. This then, these lines down here, below that are our observed actual statistic. And you'll notice they're lagging below this. Now, this is actually significant. We'll come back to why that's significant in just a minute. But so this lags below. Is that what you would expect? Think about this. Is that what you would expect for regular data? Let's go back here for a second. Imagine we had a perfect grid, and we started expanding a circle from one of the points. Something like this. Let's choose this random point. Let's say this is distance 1. Now we have our statistic right here. We have distance 1, and there is some observed, or there's some theoretical density of this right here, because that's just going to be the area of the circle right there. How many points are, for any of these, within that distance 1 of any given point? How many are within distance 1? If these are completely regular. 0, exactly. Because by distance 1, we haven't gotten there yet. We haven't gotten to the next ones. And so our actual observed is going to be 0. Let's make it 2 then. We got 2, like that. How many are within distance 2? Still gonna be 0. But our theoretical case statistic keeps ticking up. And then by 3, okay, so now we're getting a couple. So by 3, we come up a bit. If you have regularly spaced data, your K stat, or your actual K observed, is going to be lower than your expected. What would you expect it for a clustered one? How would you expect your observed case statistic to compare to your expected? Yes, it'd be higher. Why would you expect it to be higher? Yeah, so as you spread out from your original points, they're going to be clustered in close, and so your actual numbers are going to tend to be higher than what your observed is. Yes?
Depends really heavily on where your point happens.
But because we did them all pairwise, essentially we're going out from all the points. Yes. Yes?
Wouldn't it dip down though? Like when the curve would go up, if you exceed the theoretical curve and then dip down at some points?
It wouldn't dip down because this is cumulative. So,
Not dip down, but it would go off.
yes. Yeah, so you can go up and then level off.
So we kind of do the opposite, like the very first case, you kind of may go up to the line and kind of.
Yeah, so actually what you end up seeing then in this is that it goes up, and eventually this catches up like that. Yeah.
The inverse is what happens with the other.
Yep, it goes up like this and it tends to catch up. Because at some extreme distance, you're going to get all of them. Eventually, every process, whether it's random or anything else, eventually you'll get all of your points. Does that make sense?
Does it go in steps or is it like one giant step?
Well, it will go in steps. Yeah, generally you have steps. It depends on how many points you have. The fewer points you have, the harsher those or more abrupt those steps are. And the more points, the more smooth it becomes because you have more pairwise distances. Does that make sense? Okay. So let's look at what the case set actually is for this. Here is, then again, hard to see. This is our expected, and this is our observed case set. Now you notice there's actually a couple different lines here, and this is just the raw output from R. You have the couple different lines because we have different edge corrections, and it automatically plots out 3 different types of edge corrections for you, so you have slightly different things here. But you notice it's up above the line. Okay, so we're going to talk a little bit more about this. There's actually one step cooler of this where essentially expected comes out to be 0 all the time. And then I'll talk about how with the K statistic and the L statistic, we can actually end up getting statistical confidence around this. One nice thing I want to point out here is real quick before you go, the nice thing is, as I was talking before, you can have clusters, but within those clusters you have a different type of process happening, like a regular or maybe a cluster within the cluster, or like random within the cluster. You can detect that with this because it can, like, for instance, go above for a while, then go under for a while, and do these sort of things. So you can tell at different spatial distances, different kinds of processes happening. So if I have a very small scale regularness, but a large scale clumping, I can tell that with this, or different distances of t. Okay, that was a lot to digest. We'll have a little bit more of that on Wednesday, and then also some of that in the lab today. But with that, enjoy your day. I hope I didn't put you asleep at 8 a.m.